Thanks, Philip. Now, our next speaker this morning is Dr. Mehdi Azadi, who's going to talk about carbon footprint mapping. I believe he is there online.
Hello.
There you are. Okay. Thanks, Mehdi. Do you have your presentation there to share?
Sure. Just you see my screen now?
We can see your desktop.
Yep.
Okay, perfect. All right, I'll hand it over to you, Mehdi, and let you get on with it. Thanks for that.
Thank you very much. So hello everybody, and thank you for attending this session today. So this project is focused on mapping carbon footprint of mining operations and identifying mitigation and offsetting pathways for addressing this issue in the mining industry. And this is a work in progress project, which is currently being run in collaboration with my colleagues from SMI JKMRC, Associate Professor Mohsen Yahyai, Marcin Zimesky, Dr. Gordon Forbes, and Environment Center's Associate Professor Mansour Adraki, and Dr. Cara Smith from UQ Business School. So there is really no need for talking too much about the background of this topic. This is an area which is, crucial for the future of the mining industry, particularly considering the targets by the industry and the governments for the low carbon and net zero carbon footprint energy transition. So this current project is mainly aimed to address the complexities associated with mining's emissions and energy, and improving our lack of understanding and giving us a detailed knowledge of the carbon footprint intensity in mining operations to help with mapping the carbon emissions intensity within the operations, which is a very simple concept. In fact, we can't manage what we cannot measure, and also helping us with identifying pathways for offsetting opportunities and meeting the low and zero emission targets. So it's about the reason why it has been such a unclear pathways for addressing this issue is that there are so many complexities in the mining industry, which complicates this issue, such as you can see in this screen, social issues, governance, transportation, the quality of ore, changing demand, energy price, climate conditions, and so on, which all can change from a mine to another and from one commodity to other. And here in this project, we use a system thinking approach to address these complexities. So we have used a system dynamic method for this project. So just giving a quick introduction about what's system dynamics to those who might not be very familiar with. System dynamic is indeed the science of understanding the interactions between the various components of a system and how they affect the system's behavior over time, which can be a powerful tool when addressing complex problems, such as complex problems from various disciplines and origins, such as carbon emissions in mining. And one of the main advantages of, for example, system dynamics might have over traditional methods is that in system dynamic, we built a model around a problem as opposed to traditional methods where you can model a system, which is particularly powerful in mining, which deals with so many complexities. So our approach for this project has two major aims. One is focused on first mapping and accounting of the emissions at various stages of the mining operations accurately by taking into account different and specific variables controlling the emissions. And second, identifying appropriate pathways for offsetting and mitigation, which can help driving the investments and research more effectively for better outcome. So about our modeling stages and system boundaries, which we used in this work. In summary, first of all, we used a case of an example of Chilean copper mining as a case study, and looking at the copper mining supply chain. And first, we developed a material flow analysis model which captures the movement of copper from ore to metal. For example, as you can see here, you can see the copper flows from the mine, whether it's the underground source, surface mine source, or two different streams of either hydrometallurgy or pyrometallurgy to eventually to the market. And here, as you can see, here also in more simpler version shows how the copper moves from mine to market. And then next, we integrated emissions and energy streams into the model in relation to the material flow analysis model, and then evaluating mitigation and offsetting scenarios into the model. So this just shows in summary how the model is developed. So this block here, so we used a stock and flow model for first developing the material flow analysis, and this block here represents each stage of the operation. For instance, this in particular represents underground extraction, which this section is where we capture the material flow. This section is where we capture emissions. This is where we capture energy. This is where we capture mitigation pathways, as well as emissions and energy intensity. So I just wanted to go more quicker into so that I can have more time to show you the outcome of simulations and model interface so far. So go into the software. So this is the interface which shows the outcome of our simulations. So let's start. So this here shows our particular case study of copper mining, which follows the material and emissions flow during a copper mining operation. And here we have different panels. We can either start running, for example, the simulation using the initial data that we have model. And we have different panels. For example, here we can learn more, which takes us to the model, which can show us how the model is developed. And we have here shows us the total emissions, and here this panel shows us the amount of copper produced, considering the amount of production here. You may wonder why this number is 0. Here is we have used a particular data which is using a surface mine, and we used so here this particular simulation is run in a duration of 20 years. 20 years from in copper mining in Chile, and here, for example, we have some bigger picture variables that we can change here. For example, let's change the copper demand. If the copper demand was to increase by 10%, how the model will run. And here we can, let's go and have a more detailed look into the model. So as you can imagine, these 3 streams of emissions, energy, and production are very much related to one another. So here we can look at the production stream only, where it follows the amount of ore going from various stages of the operation from extraction. Here goes through the pyrometallurgy stream, concentrating, smelting, electrolytic refining, or hydrometallurgy, and all how much is produced, which goes to the market. Again, there are more some variables that we can change. Here we can just have a focus on energy distribution within this particular example, which again looks at the energy intensity and distribution throughout the process. Our focus here is on the emissions, which here shows us the distribution of the emissions within the supply chain. Again, there are some higher level variables that we can change in this particular case. Let's see if the ore grade, for example, was to be decreased by, let's say, 5%, or copper demand was to increase by 10%. Running another simulation, which shows how the emissions changes in each stages of the operation, and how that they all reflect to the totals of emission. We can also change the emission intensity in different part of the operation. Let's, for example, have a look at the ore extraction here. So here again, there are several variables which we have included here, which here we can change them to see their effect, their effect in changing the emission intensity in the operation, and their overall effect on the emissions, either both at that part of the operation, in this particular case extraction, versus the total of the emissions. Again, there are different panels here. For example, this can take us to the homepage. Or let's change some of these variables. For example, if the emission intensity due to ore grade was to increase by 10%, or by the haulage distance was to reduce by 15%, or for example, the stripping ratio was to increase, for example, by 20%, or change in hardness. So we have this for the same system set up for different stages of the operation, and there is then next stage where we can look into the offsetting and mitigation opportunities and pathways. And here we have, based on a previous work and a framework which we've developed on identifying mitigation pathways, we have identified 4 mitigation pathways, including improving, reducing fugitive emissions, improving resource efficiency, improving energy optimization, and using biological solutions, and using them as offsetting opportunities at different stages of the operation, and how they can affect the emission intensity at different parts of the operation, as well as the total emission. So let's have a look. For example, let's say if we were to improve the energy optimization by, let's say, for example, 10% in the extraction, 20%, for example, or like 15% resource efficiency, let's say, for example, 5% using biological solutions and offsetting. And actually, let's first simple model so that we can compare the differences. So let's say 15 or 10. Now let's run the simulation again. So as you can see, this reduced the emissions and the ore extraction, but considering the fact that in this particular example, the ore extraction emission is smaller versus the total of the emission, the effect wasn't very significant here. But for example, let's say if you had to improve similar improvement in smelting, which has a higher effect of a higher intensity. And in this case, you can see the effect of smelting emissions on total emissions, for example, is a lot more significant. So then there is another part, which is using considering emission caps, for example, whether it was an operational target that we wanted to reduce emissions, or was it from the regulations or legislations. So here we can have by this on and off, we can have a cap, whether we want to have a cap on total emission or each stages of operation, or we can change these emissions caps at different stages of the operation. So let's run the model once, and now let's, for example, have a look at smelting, which in this case, in this example, is the most energy intensive, emission intensive part of the operation. So currently, the highest is about 290K tons of CO2. Let's have a cap of 250, for example, for a smelting. Let's turn it off first and have a cap of about 250 and run the simulation again. So what it does in the model is that by putting that cap, it calculates the amount of material which in a smelter would be processed relevant to this much of the emission, and then this reduces that amount from the operation. So in fact, it reduces the smelting processing capacity, and therefore, as you can see here, while it does reduce the emissions, but it also reduces the amount of copper production. So it comes with a trade-off. And this is just an example of, for example, a short-term solution for reducing emission by reducing the processing capacity. But another way, for example, a mine manager or a CEO can address this is using the same money that you would lose here, and then go back to the mitigation pathway and investing it here, for example, as a more longer term solution. For example, if I were to use the same amount of money and invest it in improving a smelter's energy optimization by 15%, and then let's run the simulation again and see what happens. So as you can see, the emission, so it matches the similar amount of emission, but going back to the copper, so as you can see, we still, we kept our emissions to the same amount of 200 for the total of the emission as well as in this smelter, while producing the same amount of copper. So that's the interface that I wanted to show. Just going back to my slides. So yeah, and then so there are obviously this tool is just a usable prototype of the research opportunities which can be done in this area, and other future opportunities include things such as techno-economic studies or detailed formulation of different variables into the model, and things such as including the cost of potential evaluation of the cost of carbon or energy into the model like this, or socio-technical studies and so on. So thank you very much everyone for your attention, and please let me know if you have any questions.
Okay, thank you very much, Mehdi. That's it's always good to see somebody game to run a live simulation of their tools. So, thanks very much. We probably have time for one quick question if anybody has one here for Mehdi at all. No? Oh, Rick has one question.
I know we've discussed this before, but just almost more for the benefit of the audience. How do you see people making use of this? How do you see a company? Just what's your kind of vision for how a company might make use of this?
So the very short answer is that one is when in terms of meeting sustainability targets for reducing emissions, or one example was the one that I showed in the simulation of, for example, if you wanted to reduce emissions versus production, and that's I think it's something that needs to be integrated into the future of mining during the life of mine, from exploration to closure, when budgeting the carbon cost of the operations. But again, whether we're talking about the upstream of the operation or downstream.
Okay, well, thanks, Mehdi. Yeah. I might just add to that. When I was watching you run that simulation, I was immediately thinking of all those people out there who have projects they're thinking about developing, and thinking about what mining method they might use, etc. And I'm not sure if sort of carbon is costed yet into those sort of discounted cash flow type models yet. But when it is, I'm sure that these sorts of tools will be pretty handy.
Yeah, but also I'd like to also add to that things such as improving the energy optimization whether on a specific mine site or a whole supply chain, or a single processing plant or a single unit, which can eventually contribute to reducing the cost of the operation, as well as supporting the integration of renewables into the mining moving forward. And by identifying the economically viable pathways.